What's up, clairvoyants? Today, we're going to talk about forces in two dimensions. So, last time in the previous episode of Learning Physics Ball Z, we did kinematics in two directions. Now we're going to go ahead and examine forces in multiple directions and look at a few situations that are a little more complicated than what we looked at in the last unit. We're going to say, oh, well, what if I pull diagonally? And then we'll do some, I think, 3 problems. One of them, the very last example today, is going to be one of those problems that you'll probably see when you go to college. If you decide to carry on engaging in physics and the study of the natural world around you and mathematics and, all the other hard stuff in life. So write this down. You're going to use it later. Nothing would make me happier than if in like a year or two, you send me an email or something like that, and you say, Mr. Barton, you taught me the thing my college professor is making me do. I remember. You know what I mean? That would make me so happy. That'd be so tight. But buckle up. We're going to go on an adventure, you guys. So let's talk about forces in dose dimensions. So let me give you the pro tips first, right? We're going to give you the skinny on things we're going to be trying to do. Then we're going to go look at example problems and try and do them. So, of course, we're always going to draw a force diagram because forces, anytime forces are involved, a force diagram should be involved. And the reason you draw a force diagram is so that you can very easily write a sum of forces equation. The only difference now is that we're going to do it in both directions, even though we've kind of done that before. But some of our forces will show up in both equations. And the way we're going to get that to happen is by breaking those forces into components. Okay. I will warn you, it's very tempting to invent forces. One example, we will invent a force because it's asking us to. But there's a lot of times when I see students draw force diagrams and they put forces on them that shouldn't be there. So if you're going to put a force on it, a good rule of thumb is to make sure that you can name that force. If you can't tell me exactly what force it is or what's pushing on the object or pulling on the object, supplying that force, if you just give it some vague name, force applied, yeah, you got to be really careful with that, all right? You've got to be sure that you can justify putting that force on there. Most of the time when students are messing these up, it's messing up in this first stage of the force diagram, and they're putting just made up forces that shouldn't be on the diagram in there. Okay. Then in general, just some good advice is to pick a target variable. So this goes with like reading the last sentence first and asking yourself, what am I actually looking for? Then start looking at equations, start working to get enough information to solve for this. Usually in these problems, we're going to have to make pit stops and solve for other information first and work our way up to getting the target variable. But as always, it'll be a good time. You'll learn something. You might even have fun. All right, let's go look at an example. Let's start with some easy stuff. It says, find the missing vector. So this is one where we're going to invent a force. There is a mass with several forces being applied to it. So just some mass. It doesn't really matter how big or what it is. There is an applied force directly to the right that's 20 newtons. That's this right here. Let me change color. That's this right here. There's the weight down of 25 newtons. Okay, weight. A normal force up at 15 newtons. And a friction to the left of 5 newtons right there. So there is a fifth force on the object that makes the forces in the x and y direction balance so that the object does not accelerate. We're going to find the missing force. Okay. So let me go ahead and invent some labels for this. This specifically says applied force. So I'm going to say FA. This was called our normal force. This was called the weight in the problem. And this was called friction. They don't even tell us if it's static friction or if it's kinetic friction. So I'm just going to use lowercase f for friction in general. We don't know if the object's moving or not. We don't know how massive the object is. We don't even know if the object's on Earth. This is just a weight. We can't assume that G is 10. We could be on Mars for all we know. Things exist on Mars, right? So this problem is intentionally pretty vague just to make sure we understand what we're doing. So here is our force diagram with all the forces on there that we know. Then it's telling us there is a fifth mystery force on the object that makes the forces in the x and y directions balance so that the object does not accelerate. That doesn't mean it's not moving. It could be moving at a constant velocity. Important distinction. So let's go ahead and we can't really put it on here, right? Because we don't know what direction. Maybe it goes that way. Maybe it goes that way. Maybe it goes this way. It's hard to say. So let's go ahead and look at what we know. And then we'll put in the mystery force and solve for it. So we have a force diagram. There is a mystery force somewhere that we're not going to draw because we don't know enough about it yet. So we're going to just start in with our sum of forces equation. So let's look at our sum of forces in the x direction equals, I'm going to say to the right is positive and up is positive, like normal. So we have force applied minus the force of friction because it's to the left, plus I'm going to put Fm for mystery. I'm going to put a little x to show that this is just the x component of that applied force. And because the object does not accelerate, that is Newton's first law, telling us that the sum of forces in the x direction should be 0, so that nothing is accelerating. So we're going to set this equal to 0 because it says not accelerating. Okay. Then, before we start plugging stuff in, let's just go ahead and organize our thoughts for the y direction. The sum of forces in the y direction is equal to our normal force minus our weight plus the force mystery in the y direction. So this is actually the y component of that mystery force. The mystery force will be both of those together. It will be Fmx plus Fmy. And we're talking about like the vector addition. So we'll talk about that in a second. You can't just add the numbers because they're not in the same direction, right? But we'll talk about it in a second. So also equals 0 because, again, not accelerating. So now what we're going to do is we're going to plug in our numbers that we know and then solve for our mystery force. All right. So plugging in numbers, we have force applied is 20 newtons. Minus the force of friction is 5 newtons. Plus Fmx equals 0. Same thing for the y direction. Normal force is 15 newtons. Minus our weight of 25 newtons. Plus our mystery force in the y direction equals 0. So now we're going to solve for the mystery force. So 20 minus 5 is 15, and then we subtract the 15 over. Fmx equals negative 15 newtons. And then 15 minus 25 is negative 10. Add the 10 over. The mystery force in the y direction is positive 10 newtons. So let's just double check to make sure this makes sense. We have 20 newtons to the right, 15 to the left. This negative means to the left. If I have another 15 to the left, will that balance? Well, 5 and 15 is 20. 20, yep, that balances. Then we have positive 10. So if I have another 10 up, Will that balance? 10 and 15 is 25. 25, that balances. So we have a force that has 15 newtons to the left and then 10 newtons up. So our real force is this right here. This, of course, is 90 degrees because these are perpendicular, the x and y direction. So we know the components. It asks us find the missing force. So we want to know what is Fm. We're looking for the hypotenuse or the total force. So this means we're adding the vector components. We're not adding the numbers, right? This force is this force plus this force, so we get this diagonal line. It's like adding arrows together. So to find this number, we have to use Pythagorean theorem. So it's going to be the leg squared plus the other leg squared equals the hypotenuse squared. So we have 100 plus 225. Let me just double check my math right there. I don't want to assume something. Maybe I'm forgetting my perfect squares. I'm just going to double check before I goof it up. I'm right. Equals mystery force squared. So 325 is the mystery force squared. So we're going to take a square root and then round to, let's say, 2 decimal places to get our answer. Sorry. Of course, I've done this ahead of time, and I have an answer laying around. Let me just check my notes. It is 18.03 newtons. So we're applying a force of 18.3 newtons. That force has 15 newtons in the x direction, 10 newtons in the y direction, and is pointing like this. Like that. So this is our mystery force that we need to balance the rest of the forces. Cool. There we go. We found it. We could find the direction. Let me show you how to do that, just in case. I don't know that I'm going to necessarily test you on this, but let me... Nah. We'll do it later. It's not hard, but I don't want to overwhelm you with trigonometry. So there we go. We found the force. All right. Our next problem is dragging a box. The most common scenario, you say, Mr. Barton, I drag boxes around the house all day long. So let's drag this box. So we have a box with a mass of 4 kilograms being dragged by a rope. The rope is at an angle of 25 degrees from the horizontal. So this angle right here is 25 degrees. Given that the rope has a tension of 10 newtons, find the normal force the ground is applying to the box. Okay, so let's go ahead and calculate the normal force. Before we can do that, before we can calculate anything, we need to draw a force diagram. So here's our mass. We have, I'm going to put T for tension. And it's at a 25 degree angle, about. I'm guesstimating there. Forgive me if it's not perfect. This mass is probably on a planet. So, of course, there's going to be some weight. To counteract the weight, we need the normal force to push up from the ground. We also have, it doesn't say we don't have friction. So if I'm going to drag the box that direction, we can kind of assume that we're going to have some friction in this direction. It's not going to be super important. We're not going to solve for it, but it's important to notice that in the problem, they don't say we can ignore it. So it's safe to go ahead and put it on there. Even if we're not necessarily interested in it or calculating it or even have enough information, we should still include it in our diagram just to practice doing things completely and the correct way. So now we're asked to find this normal force. So let's go ahead and write our sum of forces in the y direction. So our sum of forces in the y direction is equal to our normal force minus our weight. And then because this tension is diagonal, this tension is pulling the box to the right. And because it's pulling a little bit up, it also has a vertical component. It's lifting the box a little bit too. So what we can do is we can take this tension and we can break it up into an x and a y component. We can call this tx and ty. What we're interested in is the y component because we're interested in solving for a force in the y direction. So what we're going to do is we're going to say, well, this is pulling up, so that would be positive. So plus the tension and just the piece of it that's pulling up. We're ignoring the part pulling horizontally. Equals, let's see. It says it's being dragged by a rope. It doesn't say that it's lifting off the ground, so we're going to go ahead and assume that this box stays on the ground and just slides horizontally. We don't know if it accelerates horizontally, but if it's staying on the ground, it's safe to assume that the acceleration in the y direction is 0 because it's not moving up or down. So we're going to set this equal to 0. Okay. So normal force is what we're looking for. That will remain a variable. Our weight is equal to the mass times the gravity of the box. So minus our mass times g. And then ty, we need to calculate this. So let's do a little aside here. Let's change colors. How about orange? So if I want ty, we know this angle here. This side is on the opposite side of the triangle. And then it tells us that the rope has a tension of 10 newtons. They're telling us this, which is the hypotenuse. So we need to ask ourselves, what trig function uses the opposite side and the hypotenuse? That's sine. We're going to set up a sine function to try and find this y component. So we have sine of the angle, which is 25 degrees, equals opposite, which is the tension in the y direction, over the hypotenuse, which is 10. So now we can solve for ty by plugging sine of 25 degrees into our calculator and then multiplying by 10 to get the 10 onto the other side. So 10 times sine of 25 degrees is equal to the tension in just the y direction. So we're going to plug that into our calculator. 10 times the sine of 25. Make sure your calculator is in degrees. If you're in a calculus class, it's probably in radians because that's how calculus usually does angles. So we get that ty equals 4.23 newtons. And I'm rounding as normal. If we have to know it to more than 2 decimal places, the problem will tell us, right? So we're not going to worry about it too much. All right, so now we have ty. So plus ty equals 0. Now that we've made our substitution for any equations and we know our values, we can go ahead and just plug in our values and then solve the problem like normal. So we're going to have our normal force is still a variable because that's what we're looking for. Mass is 4. G is 10. We're assuming we're on Earth. It doesn't say we're not. And we don't need to make this negative even though the weight is down because we've already taken care of the direction of that force with this negative sign here. Plus ty is 4.23 equals 0. Now we just simplify our math. N equals negative 40 plus 4.23 equals 0. Sorry, not equals. N minus, there we go. N negative 40 plus 4.23 is negative 35.77 equals 0. We add the 35.77 over, and N is 35.77 newtons. Positive because it is pushing up. So normally, our normal force would just be equal to our weight, but because we have this little bitty component of our tension pulling up, the ground doesn't have to supply all of that upward force on its own to counteract gravity. The rope is helping a little bit. So this little bit of help that it gets from the rope, the earth feels that and it adjusts accordingly. It says, oh, I don't need to push at 40 newtons to counteract the weight. I only need to push at 35.77 newtons. And then it just does that automatically. That's what's so great about normal forces, is they just magically adjust themselves to be whatever they're supposed to be. And you're going to say, Mr. Barton, what if it's on something squishy like Jello or a pillow or my dog? Well, worry about that when you get to college. For right now, everything's solid. We don't deal with liquids. Those things are gross anyway. If you want to deal with liquids, go to biology. All right. So that was fun. What a fun example. Now we know how hard the ground pushes. That's tight. All right. So we have one more example, and this is a very classic example that we're going to use a trick to solve. And you're going to see this trick, and your brain is going to hurt, I promise, right? You're going to be like, my brain stopped. It couldn't even. It could odd, right? It is like 1, 3, 5, 7, 9, but no 2, 4, 6, 8, right? My brain can't even. So let me help you set up the force diagram, discuss why this problem is difficult, and then we will do a very sneaky adjustment, and then the problem will magically be super easy. So it says a block on a ramp. That's this right here. There is a block of 6 kilograms on a very smooth ramp. Very smooth means no friction. The ramp has an incline of 15 degrees above horizontal. Find the normal force and the acceleration of the block. So this seems very straightforward, right? The entire problem is 2 sentences, and it's hard to imagine something much simpler than this. This is all reliable, just tilted a little bit, right? So let's go ahead and draw our force diagram. All right, condense our mass down to a point. Weight, gravity always pulls towards the center of the earth, so typically we show that with straight down. That's the weight equals the mass of the block times gravity. Here's the part that makes our lives incredibly difficult. The normal force is perpendicular to the surface the block is on. So here's the surface. Perpendicular would be this direction. Oops, let me try that one more time. This direction. So this right here, this is our normal force. And as you can see, it does not perfectly cancel out the weight. It can't, because our normal force has a vertical component and a horizontal component. This weight has no horizontal component. It has only a vertical component. So our block here is going to accelerate. Stop thinking about physics for a second. Which way is the block going to go? It's going to go sliding down the ramp in this direction. So this is a sneaky thing because our acceleration also has a horizontal component and a vertical component. That's kind of annoying, isn't it? Okay. So let's pause there, right? So you can quit writing because this is not how you should do the problem. Let me just show you how we would go about trying to do this if we try and set it up, right? I'm not even 100% sure you can do this way. I think you can, but I haven't tried it in a while, and I'm kind of at a block just like visualizing it how it would happen. But let's go ahead and look at this. So our sum of forces in the x direction, if we take this to be the positive x, this to be the positive y, our sum of forces in the x direction are going to be equal to negative the normal force in the x direction, this piece right here, negative because it's pointing to the left, equals m times acceleration in the x direction. Okay, we don't know this and we don't know this. That's a little sneaky. Okay, so we can't solve that because there's two variables in one equation. So let's go ahead and write another equation. Our sum of forces in the y direction is equal to the weight will be negative, and then we'll have our normal force in the y direction equals mass times acceleration in the y direction. All right, so we don't know this and we don't know this. So we have two equations and we have 1, 2, 3, 4 unknowns. Do you know how hard the normal force is pushing? It's not equal to weight because it's accelerating. The y piece doesn't even equal the y piece because it has a y component of acceleration, right? This problem, the way it's written, I think there is a way to solve it the way we've laid it out, but I think I'm not immediately seeing what it is. This looks incredibly challenging, right? We just don't have enough equations, and I'm not sure where we're going to get two more equations to solve this. Okay, so let me show you something that is going to absolutely blow your mind. I don't know what you're going to do, but you're going to freak out for sure. You might cry. Do you ever see something so beautiful you just cry? So let me go ahead and clean this up a little bit so that we have just the stuff we want. And I'm going to show you the magic. All right. So what we're going to do, let's go ahead and just group all this. Oops, put that back. Let's go ahead and just group all this. Stick this all together. Group. Let me go ahead and group this. Oh wait, no. Group, not ungroup. Group. Okay. And then let me go ahead and group this. We're gonna do something that's gonna blow your mind. Do this? I can. What we're gonna do is a very sneaky physicist trick. And believe me, you're gonna say, am I allowed to do that? And yes, you can, right? You guys, I'm getting antsy just thinking about how mind-blowing this is about to be for you. This is gonna be like you just saw, like, I don't know, like a picture of your grandmother in the clouds, and you're like, is that grandma? And then she like whispers in your ear, she's like, filthy axes, right? You guys, buckle up. Just put your pencils down. Take a second to chew on this. What we're gonna do is we're going to take our x and y axis. Instead of saying to the right is positive x and straight up is positive y, we're going to rotate this like that. And we're going to say perpendicular to the surface is positive y, and along the surface is positive x. So now you probably don't quite understand what just happened. Let me put this another way. Let's untilt the axes and tilt the system and our force diagram. So this, let's just level it out since I don't want to tilt my head to look at the axes. So we level out our system, we level out our axes, and of course our force diagram levels out with it. Oh my goodness. Oh my goodness, what have we done? Let's see what we've done. It might not have sunk in what we've done yet. So now our normal force only has a y component. Our acceleration only has an x component. And the thing that's being broken into components is our weight, which has now a downward component and a horizontal component. But we know the hypotenuse and we know this angle, so we can calculate both of those components. So let's go ahead and set up our force diagrams, do a little bit of trig, and then we'll show you the magic. So sum of forces in the y direction. All right. We have the normal force up, and it's just the normal force now because it's parallel to our y-axis. We don't have to say normal y because all of the normal is y. Minus the weight in the y direction. And is our block accelerating up or down from the slope, from the ramp? No. So the acceleration in the y direction is 0, and the forces balance in the y direction. Oh my goodness. Oh my goodness. So this is 0. We can calculate this, and we're looking for this. Oh my goodness. All right. Let's check our x direction. Our x direction, the normal force doesn't have any in the x. Actually, let's say, hold up. Let's take this thing. Let's just say down the ramp is positive. Why not? We have weight in the x direction equals ma. A, because all of our acceleration is in the x direction now. So we're looking for this. We know the mass, and we can calculate this very easily. Oh my goodness. So you're telling me this one equation has one unknown, so it's solvable on its own? And this equation has one unknown, so it's solvable on... This problem is done. It's easy peasy. Let's do it. All right. The hardest part of this is calculating the x and y components of our weight and figuring out what this angle is. So let's think about that really quick. Weight used to be straight down this way. And then I took the whole thing and rotated it to get this to be flat. This is 15 degrees. So I had to rotate this 15 degrees to get it to be flat. That means my weight rotated 15 degrees. So this is just that 15 degrees from the problem. So let's find our components. Weight, back up. Weight y, weight x, weight. Weight is mass times g. Our mass was 6 kilograms. So 6 times g is 10. This is 60 newtons. All right. So let's find the x first. This is the opposite side from our angle. So that'll be opposite and hypotenuse. That's sine. Sine of 15 degrees equals weight in the x direction over 60. So we multiply by 60. So let's see, 60 times the sine of 15 degrees is weight x equals 15.53 newtons. Let's calculate our weight in the y direction. This is the adjacent side. So this is adjacent. Let's use the known value, the hypotenuse. Adjacent to hypotenuse, that'll be cosine. So cosine of 15 degrees equals weight in the y direction over our hypotenuse of 60 times 60 times 60. These cancel. Weight in the y direction equals 60 times cosine of 15 degrees. This is 57.96 newtons. And now we just plug stuff in. So going back to our sum of forces in the two directions. Our normal force is what we're looking for. N minus weight in the y direction is 57.96 equals 0. Add that over. Our normal force equals 57.96 newtons. That's part of the answer we were looking for. Now we want to know the acceleration. Our weight in the x direction is Where did we hide it? There it is. 15.53 equals, the mass is 6 times A. So we do 15.53 divided by 6. A equals 2.59 meters per second squared. And we have our acceleration. Beautiful. Now that you know all your numbers, if you really wanted to break this into how fast is it traveling vertically, how fast is it traveling horizontally, or accelerating, I shouldn't say fast traveling, that's velocity. We can just go back and look at it and reverse engineer the problem, right? Here's our box. We know the acceleration is 2.59. Acceleration is a vector. We know that this is 15 degrees. So we could find AX and AY by just doing more trig and breaking this into components if we wanted to. Likewise, with our normal force, we know the size of the normal force. It's 57.96 newtons. We could just break this into a y and an x. We know this angle, it's 15. We know the hypotenuse, so we could find ny and nx if we wanted to by doing some trig. Isn't that an amazing problem? It's completely unsolvable if you just set it up with the typical up is positive y to the right is positive x. But if we tilt the axes of the system to be along the ramp, suddenly it's very easy to solve with a little bit of trigonometry. It's you guys, like, I feel like I've just given you superpowers or something. If your mind isn't just completely like whirling at the possibilities, thinking, what if I like what else is there, Mr. Barton? What else can I just tilt my head a little bit and make easier? I don't know, kids, go try it. Go explore the universe. The world is your oyster now. If you have questions, or if your mind is still whirling with possibilities and everything, go tell me about it. Be like, Mr. Barton, that was the sickest, dopest, most incredible feat of mathematics I've ever seen in my entire life. Go let me know. If you think it was super lame, if you think it was just whack, you're like, Barton, this is not that big of a deal. You just turn it a little bit. I don't know if I want you to let me know. You can let me know. That doesn't mean it's not going to break my heart, but you can let me know if you thought it was whack. I might just cry a little bit. If you want to see a grown man cry, then go ahead and let me know. But all right. Have a great day, you guys. Make sure you like and subscribe.